So, continuing our discussion on flame atomic emission, we will look at the history a little bit. Flame emission spectrometry has been in use since 1900s, almost 115 years old technology. So, combustion flames normally provide a means of converting analytes into vapor forms by supplying the energy necessary to promote the electrons from the ground state to the excited state. The intensity of the radiation emitted by these excited states while returning to ground state provides the basis for analytical method. What we want to say essentially is to we have a ground state atom here and excited state is here, and then I have an electron here, this goes to next higher energy state. If I put it in the flame, this is absorption. So, the excited atom, when it comes back to the ground state, this is ground state, this is excited state. This is the electrode we are talking about. An electron is there, and from here an electron can come back to the ground state. This is plus h mu, this is minus h mu. Okay. So, whenever there is absorption, it goes to the next higher energy state absorbing the energy. If it comes back, the energy is released. If the energy is released in the form of emission, in the form of radiation, then we have atomic emission. Okay. So, this is atomic absorption and emission phenomena. So, this is the basis for atomic absorption and emission. Now, what since we say that the technology is already there since 1900, what we want to tell you is the basic components. We will define the basic components of the system and what do they contain. I need a sample delivery system, that means I have to provide a means to convert the sample into small vapor droplets, small liquid droplets, and deliver it into the flame. That is all that is required, because flame itself can serve as a excitation source, because we know that temperatures in gases can vary from 1000 to 1200, 1500, etc. So, what we need is a sample delivery system which can which we have already described in atomic absorption, where we suck the sample and put it through a small nozzle as a spray, that is it basically. And then we need a flame as the excitation source, and it is also the emission media, because in the flame only from the flame only radiation will be coming out in all directions. So, flame is not only an excitation source, but it is also the media for emission. And then what I need? I need the optics to isolate the desired spectral lines. I do not need a huge monochromator or grating or any of those things, but a simple filter, because we know that sodium vapor lamp, as you see on the streets, it gives you only yellow light. That means all you need is a yellow filter. Similarly, if it is potassium, it needs a violet filter. So, like that we need very simple optics to isolate only the desired spectral lines. Then what we need, once the spectral line is separated from other electromagnetic radiation, we need to focus it on the detector and find out what is the current, and then what we need is a recorder, if possible. Nowadays computers will do all that kind of job. So, basically sample delivery system to be introduced into the flame, and from the flame we need the optics, a filter, common filter to separate, and then that filtered radiation should fall on the detector. All other optics and electronics etc. will remain the same. So, we will discuss a little bit about this sample delivery system. So, we have already discussed it. What we have already discussed earlier, similar considerations in AAS prevail in the flame emission system also. That is why even in atomic absorption we only have to change a switch. The most popular sample delivery system is the pneumatic nebulization, that is pass the air and then allow the pressure to come out through a nozzle which will pick up the sound. You would have seen such kinds of nebulization in your day to day life whenever you use a perfume spray. Most of the perfume sprays what we normally use after bath etc., they all contain a low boiling liquid, there is something like alcohol along with some perfume, and with a small nozzle at the top you just press it, the pressure the liquid will be sucked and then delivered through a small nozzle as a spray which we spray all around our body. So, essentially that is what we are talking about. So, the sample is introduced through a small capillary of about 5 mm diameter tube. You would have seen this 0.5 mm diameter tube in most of the perfume sprays also. So, it is to be delivered into a high velocity gas jet of the oxidant, that is in flame atomic absorption we need the flame. So, in our body this thing we just need it just sprays into the atmosphere. So, usually the gas what we need is butane in flame atomic emission FAES or acetylene as in the case of atomic absorption, and then you need some amount of air to make it burn. The dynamics of the flame we have already discussed earlier. So, in the spray system chamber larger droplets are broken down into an aerosol and the gas is carried into the burner. Typically droplets bigger than 20 micrometer diameter are collected and discarded. Okay. So, the distribution of the drop size is a function of the solvent as well as the concentration of the components. What we want to tell here is the drop size is a function of the solvent. If I use a very low boiling solvent with lot of vapor pressure, the drop size is smaller. If I use water, drop size is bigger. If I use glycerol or something like that, drop size will be still bigger. So, it is better to use water or a mixture of water and alcohols which will give you smaller drop sizes. Smaller the drop size, less is the amount of heat required to convert it into vapor. So, this is the typical breakdown of the construction of a pneumatic nebulizer. I have a liquid and then coming through a small capillary, and then I put it into an apparatus where high pressure gas flow is there. This gas flow is nothing but butane and oxidant or acetylene and oxidant, and all of them will be combining it to form a small nozzle here, okay, and this from the nozzle aerosol is generated. Very simple arrangement, and the same thing is true once the gas aerosol comes out. What happens is initially it will be something like this, and then they break down into small droplets, and the smaller droplets get carried into the flame and the bigger droplets are collected and discarded. Okay. So, the same thing modified form and more sophisticated, this we have already seen earlier. It is the nozzle, sample comes here, sample capillary, this one, and then there is fuel, there is oxidant, all of them are coming and mixing, and then there is a flow spoiler here, and then the bigger droplets are collected at the bottom of this cylinder and to waste, remaining is carried into the burner head. So, a typical flame photometer must normally therefore must be composed of a pressure regulator we need, flow meter for fuel gases, an atomizer, a burner, a mirror and slit, optical that corresponds to optical slit, optical system, and a photosensitive detector and a recording output. Nowadays microprocessor controlled instruments are available which will do most of the jobs at the push of a button or turn of a screw. So, this is the typical arrangement of a flame photometer. As I told you, you may buy a flame photometer for about 50,000 rupees with no source. You do not need a hollow cathode lamp or electrodeless discharge lamp or vapor lamp, etc. But what is required available in the market is you need an atomizer basically, and to be connected to a burner. This is the burner flame, and then this is just like a laboratory burner what you have in your laboratories, and I put a flame mirror here, reflector, and all the radiation coming backwards and other sides will be collected. This is fixed at the focal length of the mirror, and then all the radiation is passed through a prism. Okay. From the prism we have the radiation will pass through a movable slit to collect different fractions of the electromagnetic radiation. If it is sodium, it is 589, if it is potassium, it is around 600 or something like that, and for other elements there will be other wavelengths. Then I need a photocell, it has got an anode and photocell, etc. The radiation will generate photons, photons will go to the electrode of the photocell, a current will be generated which will be amplified, and detector will do the job of quantifying the current and converting it into concentration. So, this is the typical schematic diagram of a flame photometer. Okay. So, there is nothing much to tell except that this is a very simple arrangement, and most of the laboratories which are not sophisticated, especially soil laboratories, soil testing laboratories, water testing laboratories will be having a flame photometer in their laboratory. So, it is a very common instrument, but if you have atomic absorption you have this also, you do not need to buy separately a flame photometer. Okay. So, pressure regulator and flow meter are used for proper adjustment of the pressure and flow of gases. So, 10 lb gauge for the fuel and 25 lb gauge for the oxygen are required. You do not need oxygen, you can also use air, and the double diaphragm and needle valves are used to control the pressure. These are all typical mechanical details which are fixed along with the instrument, and you do not have much to do with the diaphragm and needle valves except to adjust according to the specific instructions given along with the instrument. But what we need is definitely a rotameter that is inserted in the gas line to obtain 2 to 10 feet per hour of the gas flow. The gas flow should be about 2 feet to 10 feet range. That means it can be air acetylene or it can be butane air also. Okay. So, what are the requirements of the flame? What kind of flame we do require in flame atomic emission spectrometry? First of all, the flame should possess the ability to evaporate the liquids, droplets from the sample solution, resulting in the formation of the solid residue. This the mechanism of this I have already given earlier, and it must be capable of decomposing the solid into the atoms, and it must be capable of exciting the atoms to higher energy state. So, a Mecker burner, which is quite common in laboratories, or a total combustion burner or premix or laminar flow burner. This is in AAS. Mecker burner is a bigger version of your laboratory burner, and total combustion burner is again a typical burner attached with a capillary in the at the nozzle. So, these three kinds of burners are typically used in the flame atomic emission instruments. So, what we do is we collect the radiation from the flame from a concave mirror placed behind the burner. The focal point is at the entrance of the monochromator slit. Exit slit is kept between the monochromator. You can refer the figure now, and the optical system functions as the collector, and the monochromator focuses it on the detector. Use of absorption filters or interference filters is more common in dedicated flame photometers. And we have already discussed the different kinds of filters which are glass filters, colored glass filters, or filter photometers, interference filters, which have got a band pass width of about 15 nanometers. Okay, 5 to 10 nanometer band pass width interference filters are also quite common in flame photometer. So, better isolation of the emitted radiation is the only aim in most of these flame photometers. So, that is achieved using a monochromator. You can use a prism and slit arrangement or a grating or anything you want. Quite a common experience for physics experiments, and the dedicated flame photometers use photocells. That is enough. You do not need a photomultiplier tube also, but photocell does have an amplifier unit to boost the output. But nowadays with atomic absorption instruments, photomultipliers are used. There is no need to use the photocells again separately. Photomultiplier tube will do the job in atomic absorption instruments. So, this is the typical arrangement: laminar flow burner, a concave grating, and then a line is chosen and it comes here, and this is the monochromator arrangement. And then it falls on the concave mirror, collected here on the mirror, and then again another mirror, and it comes out onto the photomultiplier tube. This is the schematic arrangement of flame emission. So, probably in the optics there will be a small switch which will change the configuration in atomic absorption instrument, but otherwise this arrangement is suitable for flame photometer also. So, a grating spectrometer equipped with a laminar flow burner and good detection readout system, as in atomic absorption, serves very well for atomic emission also. For this reason, flame emission is routinely offered as an alternate technology in most of the atomic absorption instruments. Even if you do not ask, the provision will be there in the whenever you buy an atomic absorption. since most of the wavelengths usually fall into the visible range above 500 nanometers, ultraviolet range very less, and photomultiplier tubes offer best detection limits for most of the alkali and alkaline earth metals. So, both we can use single beam and double beam flame emission spectrometers are available in the market. Of course, cost will vary depending upon what you are buying, whether it is single beam or double beam. Single beam flame spectrometers contain only one set of optics. In double beam, a second light path for light emitted by the internal standard element is added to each test solution and calibration. I think that is a little bit of more of analytical chemistry. That is, if you add an internal standard, every time you do not have to worry about the instrument setting, because with the inherent internal standard, if you get the same absorbance reading, that means the machine is performing optimally. So, signal from one detector opposes that of the other through a suitable indicating device to produce a ratio method. That is a very simple standard technique in almost all spectrophotometers, including atomic emission, atomic absorption and spectrophotometry. So, that compares the light intensities between the analyte and the internal standard. So, how do we operate the atomic emission? In the if you are using atomic absorption, you just have to change the switch and start the operation. Just like AAS also is a relative technique. That means the analysis is as good as your standards. If your standards are no good, your analysis is no good. So, depending upon what signal your standard gives, the unknown signal is compared to that of the standard, which is just like what we have discussed earlier. Prepare a calibration curve and then put your unknown and measure the absorbance and then relate it to concentration. But in atomic emission, we do not measure the absorbance, we measure the transmittance. Therefore, the standard solutions are there, they are fed into the flame sequentially and response is fitted to a linear or polynomial curve. It is not necessary that you should get only a linear curve. 99% of the time whenever you do atomic emission, you may end up with a polynomial curve. But one has to be a little careful, especially when you are preparing a calibration curve. You should either refer to the text or standard text and see what kind of response is expected for each element. So, the concentration of the element is read off from the calibration curve, that is important. So, are there no interferences or interferences? We come to the other part. Obviously, there will be interferences, but not many interferences are known to occur in the determination of alkali and alkaline earth metals. So, it is almost a specific system. Interference may also arise from the background emission due to hydroxyl and cyanogen radicals. This we have seen earlier while we are discussing the absorption, atomic absorption. This is usually in the form of a scatter which can be controlled by measuring against a matrix matching solution. So, suppose you want to determine sodium in the seawater or sodium in urine, you have to make the solution, standard solution also having almost the same ionic concentration except the analyte. So, if the sample solution is 1% salt solution, you have to prepare 1% salt solution of the standard also, but it should not contain the analyte. So, basically it is to reduce the interference from all other unwanted components of the system. So, we measure basically analyte, that is sodium, potassium, etc., and match the salts with the similar concentrations. So, this is usually in the form of that we have seen. Self adsorption can be significant at low concentration, self absorption. So, it can be significant at low concentrations. So, this I have already explained to you with the example of sodium vapor lamp in the introduction of the atomic absorption. So, this effect is more pronounced for lowest resonance line. So, operation, it is a relative technique, and then there could be some amount of chemical interference also. For example, some of the refractory oxide formation takes place that leads to incomplete dissociation, it does not melt, refractory oxides, tungsten, chromium, etc. we have discussed it earlier. So, if refractory oxide formation takes place like silicates, etc., that leads to incomplete dissociation and lower absorbance reading. But we can increase the flame temperature by another small trick, that is reducing the by addition reducing the interference by adding releasing agents. Suppose releasing agents is R. Suppose we want to analyze Mx, that is metal salt. Okay. X is the anion part, M is the cation part. I add a releasing agent. So, what happens? R will be replacing the X here. So, Rx is formed and metal ion will be released, and this addition of excess of R will shift to the reaction to the right, because it is a chemical reaction controlled by equilibrium. So, if Rx is a stable product, then metal will be more in the form of an ion. So, it leads to enhanced concentration of the gaseous metal atoms in the flame also, and that leads to enhanced transmittance reading. So, ionization we do not want, as usual. We do not want ionization because ionization causes serious interference. We want atoms, we do not want ions. That is the fundamental basis of all atomic absorption spectrometry, because if ions are formed, it is useless as far as emission and absorption. We want atoms in the ground state, it should go to next higher energy state, and the next higher energy state atoms have to come down to the ground state by loss of energy or through the emission mode. So, determination of calcium, strontium and barium in acetylene and air flame reduces the sensitivity. Why? Because calcium, strontium, barium, etc., they are all ions in solution. So, ionization causes serious interference. This can be reduced by ionization suppressant also. All chemists have got small tricks up their sleeve, especially with respect to interferences. For example, addition of potassium salts releases a large number of electrons, which combine with the ions to form the metals. So, if I add lithium salt, there will be lot of ions or potassium salts, and these ions release number of electrons, and the sensitivity of calcium, strontium and barium will increase. That means, if you want to analyze calcium, strontium and barium, we say add a little bit of potassium chloride or potassium nitrate. Okay. So, anion interference essentially acts the same way. We do not have the details here, but the additional details can be obtained by referring to the AOAC literature. Cation interference, sodium intensity doubles in presence of potassium. So, you cannot determine sodium if there is potassium also. One has to be a little careful here, what you can do is you can determine potassium first and subtract that quantity from sodium also. Okay. So, addition of radiation buffer is another trick that reduces the considerable emission from potassium. So, some of these interferences are always, it is a question of learning chemistry and applying the chemistry to the actual situations. Basically, most of the interferences what I have already told, that addition of potassium, ionization, suppression, it all leads to chemistry only. So, if you know more chemistry, you will be more conversant with the use of the atomic absorption whenever there are problem cases. If there are no problem cases, instrument will do the job. So, interference due to other element lines, emission lines is quite possible. That is, a good quality monochromator is required, other emission lines may be nearby. So, if I use a filter, emission will be more, because there will be lot of more radiation falling on the detector. So, that is a type of interference only. And then there could be interference due to salts, acids, etc. This effect can be reduced to a large extent by matrix matching. So, for example, sodium chloride interferes in the determination of zinc. Instrumental errors can happen all the time, and here there is a small error. The sodium chloride interferes in the determination of zinc. It is 213.9 nanometers. It is not 21.3.9 nanometer, but actually the wavelength range is 213.9 nanometer. Please excuse me for the error. If possible, we will correct it, otherwise you can correct it in your notes. So, instrumental errors arise from the instability of the flame, because flame itself can vary like this, and depending upon the gas flow. So, oxidant flow and gas flow should be extremely steady during a flame atomic emission measurement. So, to obtain stable flame, what do we need? The flow rate of the fuel and oxidant must be accurately controlled within plus or minus 1%. If that is not the case, then there could be certain amount of variation in the flame stability. So, the fluctuations of the detector and amplifier also leads to instrumental errors. So, we need a double beam instrument to take care of the detector and amplifier fluctuations from time to time. So, another source of analytical error, that is the atomizer function. If the nozzle gets blocked, obviously the atomic concentration in the flame will reduce of the analyte. So, we have to clean the nozzle quite often, and the capillary gets clogged due to the deposition of salts. So, sometimes regular maintenance becomes very important, because quite often you assume that everything is all right, but a small speck of dust or something like that, if it gets into the capillary, nothing will be coming out, or the sample aerosol generation itself will be different. So, in that case the transmittance readings will be different. So, with this amount of knowledge, we can look at the applications. One is qualitative analysis of alkali and alkaline earth metals, and then we can do the quantitative analysis. But flame atomic emission is extensively applied for the determination of only these elements: sodium, potassium, lithium, calcium, magnesium, strontium, barium, etc. But they are applied in the analysis of water, glass, biological fluids, petroleum products, cement, metallurgical samples, agrochemicals. The list is almost endless, including even the pharmaceuticals. If people would like to determine the sodium and potassium concentrations, typical analysis range varies from 1 to 50 ppm of the metal ions. Nowadays, there are instruments which will give you 1 to 5 ppm range very accurately. So, whenever you want to buy the flame atomic absorption emission instrument independently of atomic absorption, you should check the specifications for the calibration range for all the elements that you are buying. So, with this we will conclude our discussion on the atomic emission, and then from the next class for about 2 or 3 hours we will discuss about electrothermal atomic absorption spectrometry, which is a very good technique for the determination of elements by atomic emission, but without the flame. We do the vapor generation by heating. So, that is why it is known as electrothermal atomic absorption. So, since last 30-35 years, may not be 35, but around 25 years, this technique 30 years, this technique has gained wide popularity and commercial instruments are available that extends the determination to parts per billion level. Thank you very much.